Multiple hypothesis testing. Previously we've been discussing different inference procedures. These typically compare different populations, and they do so by comparing samples. And we build up a statistical model and make an inference from these. The thing is that this is, so far I've been telling the story out of the idea that we're measuring one variable per individual in the samples. This is often not true in biology. We are often interested in measuring multiple different variables per subject. And this has a couple of extras that introduces a couple of problems that's worth discussing on their own. So here I've modified the same scenario. We're trying to compare a healthy population with a diseased population. We do so by observing a set of samples, or we make some samples, and we observe not just one variable but a set of variables. This means that we need to create statistical models not just of a single variable but multiple variables. And then we want to make an inference regarding the difference in the populations, not just for one single variable but for multiple different variables. So these different variables could be different traits. For instance, it could be all of the different proteins you measure inside of these individuals, or it could be mRNA expressions or just genetic traits. This raises an interesting complication, and a complication that's known as the multiple hypothesis correction problem. P-values are not that informative when you are comparing multiple different hypotheses at the same time. Remember, the p-value comes from the setting that you're trying to prove that something's very unlikely given that there's no real effect. So you place yourself in a setting where there's actually no difference between case and control, or be healthy or disease, and you just see how likely would I be to observe this by random chance. And this is associated now with a very low probability we reject the hypothesis. But in this setting here, we have made multiple different observations. So say if a p-value threshold of 5%, that means that we just expect 5% of the cases to be reported with this extreme observation, or more extreme. But that's a different thing. In this setting here, we are observing multiple things. So a p-value of 5%, that was something that we just expect by chance to occur in 1 out of 20. So if we observe 20 different traits, we will expect at least one of them to have a p-value of 5%. This is a little bit like this t-shirt test here. If you think you're 1 in a million, there are 6,000 other people exactly like you. This is interesting as a joke, as actually we compare something that seems at first very unlikely, namely that you're 1 in a million, with a very large number, like 6 billion people in the universe. That means that you are actually having all of a sudden quite a number of chances to be to fulfill this thing 1 in a million. And the same thing goes with p-values. Just an example that I took from Nature is a microarray study in mice. I won't name any authors of this, but the authors were looking at some differential gene expression, and they found 77 and 642 and 2482 different expression genes at different p-value thresholds. What does that really mean? Well, actually, if you would study 50,000 probes, and you assume that there's actually no really measurement effect going on. So you measure all these 15,000 probes. How many would you be so all these probes are under null hypothesis, how many of them would we expect to be significant? Just by definition, a p-value threshold of 5% would mean that we would just multiply the 50,000 probes with 5%, and that's the number of null hypothesis we will assume would, just from definition, be reported. So this will give us 50, 500, and 2,500 different expressed null hypotheses. So actually, the reported number of genes are pretty coming in line here with the number of differentially expressed probes you expected by chance. So we need a way to correct for this. And the remedy for this is known as a false discovery rate. But before we can do this, before we can come into the definitions of a false discovery rate, let's start to think about how do we want to report this. So if we have a set of p-values that we've reported for different probes, each of these probes coming with an ID and a p-value. We understand that the lower the p-value is, the more likely the p-value is stemming from the alternative hypothesis. And the lower or the higher the p-value, the more likely it stems from null hypothesis. So we could put a threshold in this list and say that everything above this threshold we deem that significant, and everything below the threshold as non-significant. So all the probes above the threshold significant, everything below non-significant. Another terminology that you often see is that above threshold we got our true positives and we got our false positives. And below the threshold we got our false negatives and true negatives. So anything below threshold are negative calls, and everything above threshold is positive calls, and there's like false and true ones of those. So the true positives being adhering to the alternative hypothesis, and the false positives to the null hypothesis. So another way to illustrate this would be that we have, if we make a histogram after all our p-values, they would now either adhere to the null hypothesis and or the alternative hypothesis. The null hypothesis being on, by definition, being evenly distributed over the scale between 0 and 1. But it's the alternative hypothesis are more enriched towards the lower end. So we have with lower p-value, you're more likely to adhere to the alternative hypothesis. So if we now would know which ones were the alternative hypothesis and which were null hypothesis, we can easily calculate something known as the false discovery rate, and that's the expected value of the fraction of tests below the threshold x that are generated on null hypothesis. So in our case now we have a p-value score of a certain value, and above this threshold that we put on this, we can see that two of the hypotheses were on the null hypothesis, and was in total 10 different ones above or below this threshold. That means that we got 2 out of 10 incorrect, meaning that we have a false discovery rate of 20%. In practice, we never know which are actual null hypothesis and which are alternative ones, which statistics generated which. This is just a statistical argument. So instead, we need to have a way to estimate the fraction of hypotheses that are incorrect. This could be calculated now by procedure given in this paper that you will find accompanying links to, Statistical Significance in Genome-Wide Studies by John Story and Rob Tibshirani. And this is a sort of an idea where we try to, or the authors try to control for what's known as a false discovery rate, namely the number of false positive features divided by the number of significant features. And this is something that they taken from Benjamin Hochberg since 1995. Say that we have a stream of p-values from p1 to pm. It will be desirable to be able to tell now, build up a function f of t here, which is the number of null statistics below a certain threshold t. Similarly, we actually quite easily can make a function s of t that reports the number of p-values below a t-value, regardless of if they belong to the null or alternative hypothesis. So this is actually very easy to make. It's just to count the number of p-values below a certain threshold. If we would have those two functions, we can calculate the expected value of the fraction of them, namely the false cover rate. So the invention here of the paper is that the authors realized that you can calculate the number of p-values f of t as a function of just the threshold you select, because the p-values are supposed to be even, just by definition. P-values are evenly distributed on a null hypothesis. So if you know how many p-values that belongs to the null m0, then you would be able to, as well to put a threshold on this and say that every m0t, that's the number of p-values that you will see at a certain threshold. In practice, we seldom know this number, so we instead have to take the total number of null hypothesis m times t, and then multiply this with the prior probability of belonging to null hypothesis. So it becomes pi 0 mt. And a little later on, we'll learn how to estimate this pi 0. So a false cover rate is simply the number of, or the estimation of the pi 0, the prior probability, times the number of p-values times the thresholds, divided by the number of p-values you seen below a certain threshold. And that's just as easy as that. So here's a little bit more graphical explanation of the same thing, or illustration of the same thing. So if you have your p-value histogram, you can look on all the hypotheses below a certain threshold t. These either adhere to the null hypothesis or they don't. And if we can then just sort of estimate which fraction of this that belongs to the null, this red area here, which is evenly distributed over the histogram, then you will sort of know just right off the box what false cover rate you are at. So how do we estimate this thing with pi 0? Well, actually, this can be easily estimated as well, since we know that the the p-values are evenly distributed under the null. So if we look on how do the null values come out, we see that they're less of them, the higher up in p-value we walk. So if we start on a low p-value on the x-axis here, this is a p-value versus a frequency plot. If we start at a low p-value, we see less, or we see quite a number of alternative hypotheses, but the further out towards the end of this distribution, the less we see. So we can make now, in the Storch-Shirani paper, they make the estimations here based on what if these all the statistics were evenly distributed, they would be distributed according to m1 minus the threshold lambda for any particular place we look at. However, if we see a different distribution, that must be due to the fact that we have an uneven distribution and that there's alternative hypotheses involved as well. But the higher value we select for lambda, the closer to 1 we get, we get less influence from these alternative hypotheses. So if we will get closer and closer estimates of the actual pi zero. In the paper, they show this by looking at the fraction of pi or the pi zero as an estimate as a function of lambda. And as they see, the higher the lambda they select, the more variance they observe, and that's just got to do with the sample size here. The more these sort of smaller the data sizes are, the more variance you introduce in it as well. So the idea is to find in this curve where is the point where you could the variance start to increase too much, and where we can trust it, so that we still can trust it. So we could look for in this case maybe somewhere around 0.6. This seems to break down in this case, and so now the idea is then the authors just fit a cubic spline to this distribution, and they look on where does this cubic spline now hit the 1.0 of lambda. That's the estimate they use for estimation. Furthermore, they go on to define what you call a Q value, and this is a way to make to assure that each individual measurement can get a false cover rate of its own. And this is particular problem when we want to build up thresholds because often we want to make an individual threshold that's monotonically increasing with or that's increasing with the score, and so hence they make the definition that they use the Q value as being any threshold that includes the current p-value or any set, the false cover rate of any set that includes the current p-value. So it's actually, if you think about it, you could sort of make in this fictitious example here, we have a problem with the distribution of the false cover rate as a function of a score up here. So you see that with the increased score, you do not see a monotonical decrease of the false cover rate. Instead, you see a jagged behavior, so the false cover rate is jumping up and down. If we now apply a Q-value calculation on this on top of this, namely that we define the Q as the minimal false cover rate including the current point, then we will see that we sort of saw off these different peaks that appears in this data. So we get a monotonically decreasing function with the score. Okay, what I tried to tell you here is that if we make estimations based on a population or on not just one variable but multiple different variables, we need better measurements, and the way we do so is often by calculating false cover rates and Q values, and these are measures that are sort of correcting for the fact that you're looking on multiple different things. So a false cover rate is just a fraction of number of null hypotheses you expect above the threshold, and so typically you could see something like, well, I report 1,000 genes on this threshold, and I do so with a false gov rate of 5%, meaning that I expect 50 of those 1,000 genes to be incorrectly assessed.